Rain beats against the windows of a dim laboratory in Maryland, spring 1944. The world outside is at war, yet inside, silence rules. A young engineer named Charles McNary leans over a metal workbench, holding a tiny glass tube between trembling fingers. It's no longer than a man's thumb, a fragile cylinder with thin copper wires coiled inside. His superior, Dr. Merle Tuve of Johns Hopkins Applied Physics Laboratory, stands beside him. Both men know that this little object might determine whether the next wave of soldiers lives or dies. McNary whispers, "They told us this was impossible." Tuve doesn't reply. He simply watches the glass shimmer under the light, as though the future of warfare is flickering inside it. That small tube would soon be called the VT fuse, short for variable time. It was the world's first radar-triggered shell brain, a sensor that could detect a target and decide the moment to explode, without a timer or human guesswork. Before this, artillery was a lottery. Every shot relied on math, weather, and luck. Shells might burst too early or bury themselves harmlessly in mud. But with the VT fuse, a projectile could sense its own distance from the target and detonate in the air, raining fragments with terrifying accuracy. It turned chaos into calculation. The problem wasn't theory. Radar already existed, spinning in large dishes on ships and airfields. The challenge was size. Tuve's team had to compress an entire radar system, oscillator, amplifier, antenna, and power source, into a space smaller than a flashlight bulb, strong enough to survive the brutal acceleration of being fired from a gun barrel. When the shell left the muzzle, it experienced over 20,000 Gs of force, enough to crush most electronic circuits instantly. Each failed prototype meant days of shattered glass and burned copper, but also new data. Each new version, slightly tougher, slightly more stable, closer to the miracle. At one point, Navy officials almost canceled the project. "It's fantasy," they said. "Electronics can't survive that shock." Yet Tuve refused. He'd seen the possibilities. A shell that could destroy enemy planes before they reached the fleet, or strike infantry hiding beyond a hill. He persuaded the Ordnance Department to give him 3 more months. The next test, at Ardennes Proving Ground, changed everything. When the gun roared, the shell arced across the sky and exploded at precisely the right height, triggered not by time, but by the reflection of its own radio pulse bouncing off a steel target. The blast tore through the air, leaving the observers speechless. The impossible had worked. Word of the success spread through military channels with code names and caution. The fuse became restricted beyond top secret. Not even pilots using it were told how it functioned. They simply called it the new kind. In private, Tuve's engineers celebrated with instant coffee and stale donuts. Someone scribbled on the chalkboard, "The little tube that changed the math." It wasn't poetry, but it was true. What they built was more than a weapon. It was proof that knowledge could bend fate. If you value stories like this, don't forget to like and subscribe. It helps preserve forgotten chapters of history. Tell us where you're watching from and what time it is there. History connects us across every hour of the world. From a distance, it looked like nothing. A dull gray nose cone, no larger than an orange, screwed to the tip of a 5-inch shell. But inside that compact space lay one of the most intricate systems ever made for war. To understand it, imagine a radar shrunk to the size of a thimble. At its heart was a miniature oscillator, a tiny transmitter that sent out a pulse of radio energy. Wrapped around the fuse's metal casing, a narrow copper antenna acted as both sender and receiver. When the shell flew through the air, that signal radiated ahead of it, invisible and constant, waiting to bounce back from a target. The circuit was called autodyne. It listened to its own echo. When the reflected signal grew stronger, meaning the shell was closing in, the interference pattern inside the tube changed. At a precise threshold, the variation triggered a relay, which in turn ignited the detonator. The result? An explosion just a few meters from the target, not on impact, not too early. It turned a guessing game into geometry, a blind weapon into one that could see. But the science was only half the miracle. The other half was survival. Each shot from a naval gun slammed its shell forward with an acceleration of up to 20,000 times gravity. That kind of shock crushed glass, warped filaments, and snapped solder joints. To withstand it, engineers built new vacuum tubes the size of a pencil eraser, their filaments anchored by quartz stems instead of wires. Every component was locked in place with varnish and wax to absorb vibration. When early prototypes shattered, technicians cursed softly, swept up the fragments, and started again. One young woman working at the Applied Physics Laboratory recalled later, "You could hear the tubes die, a faint pop like a light bulb, and you knew it had failed." Still, the math worked. Each oscillation cycle took only microseconds, but together they formed a perfect symphony of precision. At night, the team watched tracer rounds from test guns streak across the Maryland sky, glowing arcs that ended in airbursts instead of dirt. The moment the first proximity explosion lit up the proving range, silence followed. Not from failure, but from awe. Tuve wrote in his notes that day, "We have forced radar to ride inside a bullet." Elsewhere, rumors spread quietly through the armed forces. British physicist Robert Watson Watt, the man behind early radar defenses, reportedly smiled when told of the device. "So they finally taught radar to duck recoil," he said. American engineers laughed at the phrase, but the truth struck deeper. They had turned waves into a weapon. By late 1943, prototype shells were already being shipped for naval trials. Sailors were told to treat them gently and never, under any circumstances, to open one. What they didn't know was that inside, the oscillators were hand-tuned, their frequencies adjusted within a tolerance of 1 part in 10,000. Too much variation, and the fuse would mistake the sea itself for a target. Too little, and it would sleep forever. In an age before transistors, before computers, men and women had made a machine that could think, if only for half a second, just long enough to decide the moment of detonation. The fuse that began as a laboratory miracle was still a luxury item in the winter of 1942. Early runs were hand-built, each oscillator tuned by a skilled technician, each vacuum tube cradled in wax and tested by eye. In those months, a single working unit carried a price tag of $702, a sum that could buy months of rations or a small officer's monthly pay. And production was measured in dozens, not thousands. The military could not scale a miracle. The war demanded scale. The conversion from boutique instrument to mass-produced munition was a journey of logistics and stubborn improvisation. The Applied Physics Laboratory at Johns Hopkins sent sealed blueprints and a handful of prototypes to manufacturers. Crosley and Cincinnati began tooling in September 1942. Eastman Kodak in Rochester adapted its precision optical lines, Sylvania and RCA reworked tube shops, and General Electric retooled machine floors for tiny metal parts. A small convoy, engineers, sealed crates, and a military courier traveled from Laurel, Maryland to those plants, a route that threaded university labs to Midwestern factory towns. Each stop meant new problems. Machinists who had never dealt with glass vacuum tubes, supply clerks scrambling for mica and silver paste, and foremen who had to train thousands of unskilled hands overnight. The industrial problem was twofold: make the parts cheaply and make them endure 20,000 G of firing shock. The breakthrough was process engineering more than pure invention. Manufacturers introduced printed circuit techniques and new shock-hardening molding compounds. Tube filaments were anchored to quartz stems and sockets were potted in resin. Lines of women inspectors, nicknamed tube angels in one Crossley plant, sat at benches with microscopes, checking filaments and solder beads, passing jars of black coffee and snippets of gossip about boyfriends on leave. One forewoman later remembered the rhythm. We whispered when the boss came by, cursed when a batch failed, and cheered when the daily count climbed. Those small rituals kept an assembly line secret moving at wartime speed. As volume rose, cost fell with a cruel arithmetic. Procurement that had been counted in hundreds became millions. By 1943, output crept into the tens of thousands per day. By late 1943, production reportedly approached 40,000 fuses daily, and by 1945, factories on hundreds of lines were turning out as many as 70,000 units a day, driving the unit cost down to approximately 18. The government spent roughly $1,1945 to procure about 22 million fuses by war's end, a staggering sum that, crucially, bought a new kind of precision at scale. Human moments threaded through these numbers. A young machinist in Rochester stapled his payslip to a letter he mailed home and wrote, "We make little tubes that kill planes today. I can't tell Ma, but I keep her picture on the bench." While an Eastman Kodak quality inspector kept a scrap of a child's drawing beneath her microscope as a talisman against the fatigue. The industrial march that cut the unit price from hundreds to teens did not erase the small private costs, exhausted shifts, split families, and the everyday gamble that one faulty solder joint might mean a splintered ship or a saved life. The arithmetic was decisive. What had been too rare to matter became ubiquitous enough to change tactics, and the price drop from $732 to $18 between 1942 and 1945 is the single ledger line that explains how an experimental miracle became a strategic weapon. October 1944, Leyte Gulf. April to June 1945, Okinawa. Two names that naval men will never forget. The Pacific had become a theater of desperate flights and steeper stakes. As the American fleet closed on the Philippines and later scrambled to hold Okinawa, a new threat took shape in the skies. The kamikaze, a pilot who turned his plane into a missile and aimed himself at steel and men. Against that human torpedo, traditional point-blank gunnery was often too little, too late. The sky needed a weapon that could detonate before the airplane struck. The VT fuse supplied exactly that moment. On the morning of October 1944, after the chaos of Leyte, gunners on escort carriers and destroyers began loading 5-inch shells fitted with the new fuses. The ship's log of USS Banshee, scratched in pencil, oil-smudged, recorded a scene that would repeat itself across the Pacific. 0932, bogey bearing 230, airburst observed 200 yards off bow, plane shredded, many small fragments. The entry is brief, but it carries the weight of a saved crew. Admiral Arleigh Burke watched these early tests and understood their implication. He would later write about the way airbursts changed a ship's fate. What had once been a target that pilots could plow into became a moving minefield. In the gunner's world, the proximity burst was a force multiplier. Where a contact fuse required a direct strike and a time fuse needed a well-calculated fuse setting, the VT fuse created a cloud of lethal fragments at the best possible standoff. Against fast, diving aircraft, That cloud was often the difference between a crippled plane and a foundering ship. The statistics of the moment are stark in the gunner's after-action reports, where previously an average destroyer might hope for a single plane kill per dozens of rounds. Post-VT trials in the Pacific often reported 2 to 5-fold increases in effective interceptions by medium and heavy AA batteries when proximity fuses were used on 5-inch and 40-millimeter projectiles. One gun captain noted that the bursts come like a curtain. He never reaches the hull. These multipliers transformed tactical calculus. Convoys could hold position, carriers could recover attack planes without the same fear of losing decks to a single suicidal strike. Human details make the statistic concrete. A young gunner, Petty Officer First Class Thomas Miller, wrote that night in a pocket diary, "We watched him come, thin smoke, a shadow over the water. Then the sky lit, and the plane folded like paper. I kept my hand on the rail for hours after, and my palms still shook." Bosun, a chief petty officer, later tucked that diary into the pocket of an oil-stained jacket and kept it for the rest of his life. It ended up as a short entry in a Naval Museum file labeled, "Saved by the Airburst." There were moments of strange guilt and awe. Sailors watched whole squadrons of attackers shredded in mid-descent and felt the moral sharpness of a machine that decided to kill before impact. The psychological contrast was vivid. Once, crews faced the horror of an airplane smashing into wood and steel. Now they watched the sky itself fracture the attack. For some, the fuse felt like a miracle. For others, like an unforgiving arbiter. On the night watch at Okinawa, one radar operator recalled seeing a phantom of tracer and sparks and writing simply, "The sea glowed with falling pieces." That image, falling fragments like artificial stars, became a symbol of how technology could both protect and remap the brutality of combat. In that remapping, the VT fuse did not remove the violence. It changed its geometry. Where pilots once found a way through, they now met a ceiling of shrapnel that arrived before their engines could scream into the hull. Winter 1944 Belgium. The snow was so thick that gun crews at the edge of the Ardennes could barely see 10 yards ahead. The Battle of the Bulge had begun, and the German army was pushing with everything it had left, tanks, mortars, and men hidden under the forest canopy. For days, American gunners had fired blindly into the woods, listening to the echoes, trying to guess where the enemy was moving. Then the crates arrived, stamped VT fuse, handle carefully. The crews didn't know what those letters meant, only that the new shells were supposed to burst in air. They called them smart shells, or sometimes sky mines. By dawn, the first batteries of the 2nd Armored Division were ready. Sergeant Leonard Klein, who had fired hundreds of timed rounds before, later recalled, "We began to see bursts right over them, not on the ground. It was like the trees themselves exploded." The proximity fuses changed everything. Instead of exploding after impact, each round sensed the earth and the men below, detonating 30 or 40 feet above. The shrapnel fanned downward in a deadly cone, cutting through helmets and tree trunks alike. Within hours, whole German companies were pinned in place, stunned by a weapon they couldn't understand. One Wehrmacht officer captured later wrote in his field notebook, "The Americans have shells that know when to burst. Even the air turns against us." Artillery officers had long treated timing as an art, counting seconds, measuring angles, predicting wind. The VT fuse made timing automatic, perfect, merciless. Reports from the 406th Field Artillery Group show that their kill efficiency doubled within the first 24 hours of deployment. At Bastogne, proximity shells forced German infantry to abandon their concealment. Snow-covered branches turned into lethal splinters, and the front line began to shift. Yet the soldiers who pulled the lanyards weren't thinking about science. They were cold, sleepless, and half-deaf from the roar of their own guns. Between salvos, they brewed coffee over powder tins and wrote letters home. One corporal named Franklin wrote to his wife, "There's something new in our shells, something that makes them burst right where they should. Don't ask me how, just know it's saving us." Not everyone celebrated. Some men whispered that the new fuse made killing too easy, too detached. There was no longer any need to see the enemy, only to feed coordinates into the machine. But in war, perfection is survival. By New Year's Day 1945, the fuse had turned artillery into a precision area weapon, and the bulge, Hitler's last gamble, began to collapse. Afterward, engineers back in Maryland read the field reports in silence. Two of his team underlined the phrases "burst in trees" and "cleared positions instantly." One note in the margin simply said, "It worked." They had built a device that could end battles faster and spare their own troops, but it was impossible to ignore what that also meant. A single adjustment in a circuit could change the mathematics of death itself. Before moving on, a question to you, the viewer. If a machine could choose the perfect moment to explode, would that make war more humane or just more efficient? The victory of a circuit often began in the hum of a factory lunchroom. In Rochester, Cincinnati, and across a dozen Midwestern towns, assembly lines smelled of oil, coffee, and blown glass. A network of suppliers, Crossley, RCA, Eastman Kodak, Sylvania, General Electric, and dozens of small subcontractors, stitched the VT fuse together like a vast mechanical quilt. Raw mica came from the Southwest. Silver paste and filament wire arrived by rail from Cleveland. Insulating resins were compounded in small chemical plants and trucked under blackout conditions to machine shops that had never before made military parts. Maps in ordnance offices showed clusters of dots across the United States, machine shops, tube houses, varnish plants, testing ranges. Each dot was a hinge in a logistical chain that turned science into ammunition. The scale was dizzying. At peak production in 1944-45, some estimates put the number of factories and subcontractors involved at over 75 distinct plants, employing well over 100,000 workers on VT-related lines. Daily output on aggregating lines could reach tens of thousands of fuses per day. Annually, the program pushed toward millions of finished units. A government procurement ledger later summarized the cost and effect: massive capital, tiny unit price, enormous strategic return. The arithmetic was simple and brutal. Make enough, push cost down, and the weapon moves from novelty to doctrine. Inside the plants, women made the difference. They held filaments under microscopes, soldered beads no larger than pepper grains, potted sockets in resin, and taped antennas with hands that learned new dexterity by repetition. A forewoman named Evelyn kept a scrap of a child's drawing in her pocket as she inspected tubes. A machinist named Joe from Rochester would swallow his lunch quickly to catch an extra hour on the lathe. They argued about shift schedules, laughed at gossip about a foreman's new wife, and sometimes wept when a batch failed final shock tests. One inspector later left a 2-line note in a veteran's oral history. "We knew we were making something special. We did not like knowing what it would be used for." Process innovation, not a single heroic invention, drove the price down. Engineers introduced printed wiring where hand-wired leads once ruled, automated jigs that held tubes steady during soldering, and new shock-hardening compounds that absorbed muzzle shock instead of transferring it. Testing moved from sporadic laboratory trials to statistical quality control. Sample batches, shock racks, and firing tests at proving grounds. When a plant reported a failure rate drop from 12% to under 1%, its managers marked the floor with a small flag and treated the day like a minor holiday. The logistical journey could read like a small novel. A crate of tuned oscillators left Baltimore by night, crossed an industrial state, and arrived at a Rochester plant where an Eastman Kodak machinist would mount it in a nose assembly. That assembly traveled next to a Sylvania plant for final tube sealing, then to a Crossley bench for tuning, and finally to a naval inspection station where a white-gloved technician watched a tiny needle swing on a frequency meter. At each handoff, a signature was required. The chain of custody was a promise that the tiny device would survive more than a heliograph of engineering. It would survive a cannon's throat. And yet, for all that scale and precision, there were human contradictions. Women who polished the glass remembered their sons and husbands on the docks. Men who welded the nose cones cheered when a ship's log reported a kamikaze deflected by an airburst. They felt pride and unease in the same breath. One short letter tucked into an archive read, "I sew seams in fuses by day and mend my sister's coat by night. We keep doing both because there is no other work like this." When asked later whether industry had made the war more humane by shortening battles, many of these workers smiled and said only, "We did our job." What would you do if your daily labor could shorten a war, but made you complicit in its deadlier math? When the guns finally fell silent in 1945, a strange stillness replaced the fury of production. The factories that had once vibrated with assembly lines of glass and copper were now empty, their benches swept clean of filings and solder. On one of those benches in Cincinnati, a forewoman named Evelyn packed a single fuse into a small wooden box, wrapped it in cloth, and wrote on the lid, $18. And it saved more lives than I'll ever know. The war's closing months had proven the fuse's worth beyond all debate. On destroyers off Okinawa, it had slashed kamikaze hits by nearly 75% compared to earlier campaigns. On the Western Front, it shortened artillery engagements and shattered German counterattacks before they could regroup. Military analysts would later write that the proximity fuse added as much to victory as radar and the atomic bomb. But for those who had built or used it, the achievement felt quieter, almost fragile, like the glass tubes themselves. As demobilization began, thousands of workers returned to normal lives. Crossley went back to making radios, Kodak to film, Sylvania to light bulbs. The scientists who had wrestled radar into a bullet turned to peacetime research. Tuve returned to cosmic ray studies, Lyman Briggs to atomic standards. Yet the lessons of the fuse never left them. That precision could grow from patience, and that the smallest instruments could alter history more than any roar of engines. In 1946, when Congress publicly honored the team, Tuve refused a medal, saying only, "It was done by thousands of hands, not mine." Years later, in the Smithsonian's National Air and Space Museum, a display case appeared labeled, "The Fuse That Thought." Inside, a single VT unit sat beside its 5-inch shell casing, wires gleaming faintly under museum light. Veterans would stop before it and stare longer than tourists expected. One old gunner, now stooped with age, tapped the glass gently and said to his grandson, "That little thing made the sky safer. We didn't understand how, but we trusted it." He wasn't alone. Letters preserved in naval archives show a recurring theme, gratitude mixed with awe. "We never saw who built them," wrote one sailor, "but we owed them our tomorrows." For every scientist calculating circuits, there had been a machinist polishing filaments, and for every gunner pulling a lanyard, an unseen engineer somewhere far from the front line. The proximity fuse's story ends not with explosions, but with reflection. It was a device that measured distance between shell and target, between fear and survival, and in doing so, it quietly measured the distance between human intention and technological power. In the end, the small glass brain had done more than change the math of war. It had forced humanity to reckon with the cost of precision itself. Decades have passed, but the echoes of that little fuse still resonate in every guided weapon that came after. Each radar lock, each smart missile, each laser trigger carries a trace of the same idea born in those Maryland labs, that timing and awareness could make war cleaner, more controlled. Yet the irony lingers. In seeking control, mankind made killing more exact. Still, there is another legacy, softer and easily overlooked. For many of those who built the fuse, it represented faith. That knowledge could save, not just destroy. The same hands that wired miniature oscillators later wired hospital instruments, weather radars, and spacecraft sensors. Out of destruction came a discipline that would shape peace. In an old diary found among Tuvey's papers, one line stands out. If we can teach a shell to think, perhaps one day we can teach ourselves to stop. That sentence, scrawled in fading ink, feels like the true ending. Some inventions roar into history, others hum quietly in glass and wire. The VT fuse belonged to the latter kind. A whisper that changed the language of war. A fragment of science that made the world both safer and more complicated. Its story reminds us that progress is never innocent, but it can be luminous. Like the brief pulse of radar inside a tiny tube, flickering once, perfectly, before fading into silence.